Next, really quickly on exit ticket grading. In terms of exit tickets, all I care about is line by line computation and that you have your answer boxed. So I just want you to show your work. And then for exit tickets on Google Forms that are just like multiple choice, obviously you don't need to show your work in that case. In that case, it would just be a completion grade. On a random date each week, I'm going to grade a do now instead of an exit ticket, and that just to the do now. And I want to make sure people are putting effort into that. Tickets are going to be worth 5 points each, and same deal with class notes. Late exit tickets and late do nows will still be able to receive partial credit. Cool. And then I'm going to give everyone 1 minute or so to set up their notebooks. So today we're going to be doing our first day of related rates, which is probably one of the tougher topics. I'm not exactly sure what you guys have covered, to be honest, in your previous class, but I would say this is one of the tougher topics in calculus, like differential calculus in general. So we're going to spend actually 3 or 4 days on related rates, and today will be our first day. Please get your notebook set up. And then as you get your notebook set up, also a quick reminder, the homework packet was uploaded this weekend and it's going to be due Friday at midnight. So the homework packet, I don't think it's too difficult. I think it's one of those things where if you do 2 or 3 problems a day, and it might take 20 to 30 minutes, like you should be able to consistently finish and not have to worry about it Friday. If you have questions, feel free to email or message me again. Again, I'm totally open. And then also I will be trying to upload like videos over the week to help with the homework packet. So if you guys have taken a look at it, I feel like most people probably haven't started on it yet, which is totally fine. But if you do a couple problems a day, I think you should work through it pretty consistently and you'll be fine. And a lot of the problems are very similar to problems we've worked on in class. So just a quick reminder on that. Okay. So I'm going to, oops. Go over the do now. So the header today will be unit 5.1/5.2 related rates, day 1. So again, take like 10 seconds to copy that if you need to. Okay, so Reese asked if these are the notes, if you're reviewing. You don't really have to include this in your notes. I was hoping like as you're writing down for the do now, this would kind of just be an extension of your do now notes, but you don't have to draw the graph or anything. So the first question here is we're going to be looking at what the average rate of change is for the interval from 2 to 5. Looking at the do now, I think people actually struggled with this quite a bit. So the average rate of change, I'll just go over it. I'll just review this concept really quick. So the average rate of change is like when you have a function like this, right? And from 2 to 5, you want to find the average rate of change. That just means finding the slope of the secant line from 2 to 5. So I think it might be clear. Let's say it's from 2 to 10. We notice that the rate of change, it changes like pretty consistently, right? Like the graph might be curved like this or that, but we don't care. We just care about the average rate of change, which will always be just a straight line, and we're going to find the slope of that line. So the equation for the slope of the average rate of change is simply, we're going to do slope. As you guys all know, that is equal to rise over run, or change in y over change in x. In this case, we can think of it as the slope of the secant line. So it's f of b minus f of a over b minus a. So basically, we're just finding the change in y over change in x. So how do we do this? So we're going to plug in 5 into 1 over 10 f squared, because that's our function, right? So let's say f of 5 minus f of 2 over 5 minus 2 is equal to, so we'll plug in 5, 1 over 10 times 5 squared, minus, now we're going to plug in 2, 1 over 10 times 2 squared, all over 5 minus 2, because we're doing b minus a. So this is essentially just change in y over change in x, right? So by plugging in 5, we're going to get this y value. By plugging in 2, we're going to get this y value. And then the change in that y value is this. And the change in the x value is in the denominator. 5 minus 2 is this. So we're finding the change in y over the change in x. And then this gets us the slope of this line, which is the average rate of change. So this tells us on average, well, the penguin population is increasing on average by, here, I'll just solve for this really quick. The answer that we ultimately get is 21 over 30, or 0.7. So our average rate of change is that the penguin population is increases by 0.7 thousand per 1,000 fish. And this is like important just because we're applying this concept of slopes and rates of change to actual problems. And the average rate of change is an important concept for us to review. So I'll give everyone like 15 more seconds just to copy the work down for this. Okay, cool. So now for the second question, what is the instantaneous rate of change at t equals 4? I gave a hint in the do now that it's just the derivative. I noticed Daniel typed something in the chat. Would you want to come off mute and type and explain kind of what you typed in the chat, Daniel? Okay, Daniel seemingly isn't there right now. Did anyone have an answer for the instantaneous rate of change? Like how they thought about this problem? And Alexandria, I see that you shared something else for number 1. Thank you for that. I'm just going to try to move on to the second question for now. Okay, I'm going to cold call on Reese. Would you be able to come off mute and kind of explain what you thought about the second problem?
So for the second problem, can you go back up so I can see it?
Oh yeah, sorry.
The second problem, I went to t equals 4, and I try to figure out the rate of change. And t equals 4, so I didn't know what to do after that. I honestly don't know like how to do it, but I think just substitute in or try to find like what is going on at t equals 4.
Okay, sounds good. Thank you for that. Yeah, so that would be a good first step, is just going to t equals 4 and then kind of, here, I'll erase this work, but going to t equals 4, and you can kind of see the rate of change here. You can maybe estimate it. It looks like it's positive and it's like close to 1, something like that. But for us to find it exactly, the instantaneous rate of change is always just the derivative. So that's something, that's like an association we really have to make. Derivatives just gives us, like, tell us rates of change. So the average rate of change that we looked at in the first problem is like kind of related to this concept of derivatives. It's just more primitive, I guess, because we're just finding slopes, right? We're just really plugging in numbers. And derivatives allow us to find the slope at this precise point. So the average rate of change in this first problem, it allows us to find like the slope of this, right? Of like a big difference, let's say from here to here. A derivative tells us what the slope is right at this point, or like right at that point. It can tell us that exactly. And the way we do that is simply deriving the function that we're given. And this actually is a typo. This should be f. So I'm not sure if people were confused by that, but it's f and not t. But if we derive 10f, 1 over 10 f squared, so I believe p of f is equal to 1 over 10 f squared. So p prime of f, so this is the derivative, and this will tell us instantaneous rate of change. Right, so again, p of f is a function that tells us for however many fish there are, it tells us we input like the population of fish and it tells us the penguin population, right? And that makes sense. The more fish there are, the more penguins there will be, because they can survive on the fish. But the rate of the penguin population growth, depending on the fish, we can find that by finding the derivative of the function. So the derivative of 1 over 10 f squared is going to be power rule, so we bring the 2 down, so 2 over 10 f, or it's just equal to 1/5 f. now we have this function that's the derivative. To find the instantaneous rate of change at that point, though, we just plug in 4. So we're going to plug in 4. We're going to get 1 over 5 times 4. We're going to get 4 over 5 or 0.8. So the instantaneous rate of change at when there's 4,000 fish, the penguin population is increasing by 0.8 thousand per 1,000 fish. That makes sense. So I'm going to give everyone 20 seconds or so to copy this point down. And I'll just try to clarify what this means. So the 0.8 is 0.8 thousand penguins. So I'm gonna write that as 800, because 0.8 thousand is 800. 800 penguins per 1,000 fish. So going back to this problem, we see that the penguin population is increasing as the fish population increases, right? As fish increases, the penguin population also increases. But the question is how much? Well, at this point, at f equals 4, we figured out that as the fish population increases per 1,000, the penguin population is increasing by 800. So that's what that instantaneous rate of change tells us. That's what the derivative tells us. So yeah. Okay, I'll give another 15 seconds or so. There's 10 more seconds to copy that down. Cool, and then this helps us anchor down just our key stamp or key takeaway for this section of today's lesson, which is that the average rate of change can be calculated by the equation f of b minus f of a over b minus a, which is really just change in y over change in x. And it's really just a slope. We're looking at the slope of a secant line. And then next, we're going to compare that to the instantaneous rate of change. And this is where, like, again, just to reiterate, like, calculus A is most interesting. It's looking at instantaneous rate of change so we can tell exactly what the rate of change is at a specific point. And that is just the derivative. So that's basically why derivatives are useful, why we care about like power rule, chain rule, all these different rules to find the derivative is so like for these functions, we can find the instantaneous rate of change. And again, derivatives, so f prime of x, dy dx, they all kind of mean the same thing. It's the derivative at a point. And again, that's the instantaneous rate of change. So yeah, I'll give everyone 15 more seconds or so to copy this all down. And just to make sure we have this clear, I'm going to cold call on a student just to kind of clarify what the average rate of change is and the instantaneous rate of change is. Samantha, would you be able to come off mute and just kind of clarify the concept in your own words?
Wait, clarify the concept of average rate of change or instantaneous rate of change?
Yeah, both of them if possible.
Oh, basically, the average rate of change is basically, it's based on, the original graph we're given, but the instantaneous rate of change is based on the slope at that specific point, but in order to find that, we need to find the derivative at that point.
Yeah, great. So I think your summary for the derivative is perfect. So we're basically using the derivative to find this slope at a specific point. So you guys are probably all familiar with looking at this as like the slope of a tangent line, the instantaneous rate of change, the derivative, they're all related. The average rate of change, again, is when we're looking at a secant line. So that's when it crosses the graph at 2 points. And it's kind of more like a rough estimate. Let's say we want to find the slope at 5, we can kind of estimate the slope again through a secant line, but this isn't perfect because it's not the instantaneous rate of change. It'd be the average rate of change between 2 points that can kind of help us estimate what the slope would be. So again, in calculus, we're mainly concerned with this, the instantaneous rate of change, derivatives, slopes, etc. But thank you for that, Samantha.
What happened?
Awesome. So, sorry, go ahead.
Oh, I thought you said something. Sorry. Never mind.
Oh, no, I was just thanking you. Thank you for sharing. Yeah. So now we're going to move on to a quick review of geometry. This is going to be important in our next big topic, which I talked about earlier, which is related rates. So I'm going to give everyone, I'm going to minimize this some more really quick. I'm going to give everyone 8 minutes or so to solve as many of these problems as they can. All of the equations that you'll need are up here. And then, yeah, all of the equations you'll need are up there. So I'm going to give everyone 8 minutes just to kind of refresh their memory on geometric equations that they may have forgotten earlier. But we're going to need to remember them for related rates problems because we're going to be using a lot of these. So please begin now. You'll have, I'll give 7 minutes actually. So please begin now. Once you complete all 10 questions, just chat your name in the chat, just so I know you're done. And then we're gonna really quickly go through each of the problems, and I'll probably cold call on students to quickly share their answer and the equation they used. And just provide some clarification for your notes. I'm not going to expect you to write each of these questions down. Just like if you want to number each of the questions and show your work, that'll be plenty. These aren't really a critical part of like any concepts or anything like that, mostly just for drilling and review. So. Around 3 more minutes or so. Thank you, Samantha. Around 1 more minute, and then we're just going to work through these really quickly. I'm going to probably just go down the list and call on students for each problem. Awesome. Thanks for finishing up, Aaron. Great job. Cool. Just 30 more seconds or so. And then we're going to try to speed through these. Oh, yeah. Aaron asked that he specified that he put his work on a separate piece of paper and whether you need work for this part. If you're asking about for the class notes to turn in, honestly, for this part, if you don't turn in like the class notes, that's totally fine. This is more just for you guys to practice using geometric formulas and just like refamiliarize yourself with them. Okay. So let's start working through the problems now. You might notice that if you're taking notes on the PDF sheet, there's like boxes down here to write on. I don't think I'll be able to show both the equations and the boxes on the same sheet. So I'm just gonna write down the equations and answers here. So for the first problem, Aaliyah, would you be able to come off mute and really quickly give the equation that you used and your answer?
All right. I used 1/2 times base times height.
Cool. And then what was your answer?
And I got 18.
Yep, that's exactly right. So 1/2 base times height, we see that the base of the triangle is 3. So we multiply by 3. The height is 12. That's 36 times 1/2. We're going to get 18. Thank you. Aram, could you come off mute and give your equation and your answer for the second problem?
For number 2, I used a squared plus b squared equals c squared.
Awesome. And what was your answer?
My answer was 5.
Cool. Yeah. So anytime you see a problem with the right triangle, you're probably going to want to use the a squared plus b squared equals c squared equation. So again, the a squared plus b squared equals c squared equation, Pythagorean theorem, basically uses the 2 legs of the triangle to give us the hypotenuse of the triangle. So the hypotenuse is the longer side. But we get a squared plus b squared equals c squared. And we have the 2 legs are 3 and 4, so 3 squared plus 4 squared equals c squared. This all equals to 25 is equal to c squared, so c is equal to 5. Cool. Alexandria, could you come off mute and do number 3 for us? Again, just the equation and your answer.
Okay. Number 3, you said?
Yes.
Okay, this is oh no, I was actually struggling on that. Oh wait, I think I said 486, but I think that's wrong. I don't know.
Okay. Yeah. Well, could you explain like your thought process for it? How did you get to that number?
I don't know. Like, I did 3. Oh, I did 6a squared.
Oh, that's actually the right method, I think. So you had each side is 3, right?
Yes.
Of a square. Okay, so one way to think about it, I think, is so the area of a square would be a squared, just like you said, right? So 6a squared. A squared is the area of a square if a is one side. So we're going to have, oh, sorry. So 3 squared, and then you multiplied it by 6 because there's 6 sides for a cube. So we're basically taking the area of the square and multiplying it by 6 because it's a cube and not some other shape. So this times 6, but we're ultimately going to get 9 times 6, so that's 54. So the right answer for this is 54. Ansel, could you come off mute and do number 4 for us?
Number 4?
Yes.
I got 49 pi.
49 pi, cool. And what was the equation that you used?
It was a equals pi r squared, and I just plugged in the radius.
Okay, cool. Yeah, that's exactly right. So pi r squared, we have the radius is 7. So we're going to get 49 pi. Cool. Christian, could you actually come off mute and do number 7 for us?
I used 2 pi r, and I got 14 pi.
Sorry, number 7, not number 5. Sorry, I'm skipping a bit down because for the sake of time.
1/3 pi r squared times h, right? And I got 4 pi.
Okay, yeah, that's exactly right. So this might be an equation that people aren't familiar with, like just right off their memory or anything. But it tells us specifically the volume of a cone is 1/3 pi r squared times height. So we just plug everything in. 2 squared, height is 3. So we're going to get, 3's cancel out, so we're going to get 4 pi. Let's see. Derek, could you come off mute and do number 9 for us, for how many radians are in a quarter circle?
Oh, I'm not sure. Number 8.
Sorry, your mic was kind of like rough. Could you try to repeat what you said?
I said I'm not sure. I stopped at number 8.
Okay. Okay, that's totally fine. Thanks. How about Samantha or Damani? You actually volunteered in the chat, so thank you, Damani, for volunteering. Go ahead and do number 9.
So I got pi over 2 because I did 2 pi times 1 over 4. So I got pi over 2.
Gotcha. Wait, so could you reiterate how you did? You did 2 pi times what?
Times 1 over 4 because that's a quarter.
Yep. Okay, that's exactly right. So I think the one rule, if you can't exactly remember for radians, is to always remember that in a full circle, there are 2 pi radians, and then through this you can basically brute force your calculation for like any of the other specific like radian values that you need to know, as long as you know that 2 pi is a full circle or 2 pi is equal to 360 degrees. So for a quarter circle, Damani, you did it exactly right. We multiplied by 1/4. So we're going to get pi over 2. Yeah, and then if you want to do like 30 degrees, let's say 30 degrees is 1/12 of 360, you can multiply this by 1/12 and get pi over 6 for 30 degrees. And that can be really useful if you like forget your unit circle stuff from trig. So just remember that 2 pi is a full circle or 360 degrees. So thank you for everyone who participated in the review for like our geometric equations and stuff. Unfortunately, we weren't able to get to an example related rates problem today. That's totally fine. They actually take somewhat of a long time to get into. They're probably one of the more difficult topics. So we're gonna tackle that tomorrow. Besides that, just remember the usual stuff of having your exit ticket turned in by 10 p.m. and also a picture of your class notes by 10 p.m. and start working on the homework packet that I assigned this past weekend, if possible. Like I said at the beginning of class, if you work through 2 or 3 problems a day, you should be able to finish it with no problem. So try to get working on that so you don't have to cram. And I am always open for any messages or concerns or questions you have. So just email me or text me with that. And thank you all. And I will see you tomorrow for our next class. Thanks, everyone. I'm going to stay for a bit after class for anyone who has questions. So feel free to stay after class. Hey Reese, hey Damani, how you guys doing?
I'm good. I'm about to do the exit ticket.
Sorry, what'd you say?
I said I was about to do the exit ticket, like I'm getting ready to do the exit ticket.
Oh, okay, okay. Sorry, I thought you had a question. Okay, go ahead. All right. Thanks for coming then. I'll see you tomorrow then.
All right.
Thanks, Reese.